As I was telling, RSVP is not a routing protocol. It is a resource reservation protocol. See, if someone do not know the route, how can they reserve the path? If a protocol do not know the route to reach the destination, how can it reserve path? That's a point that we need to get an answer. What is RSVP, Resource Reservation Protocol? It works along with MPLS. What is the job it accomplishes? It is going to block some resource from point A to point B, from in between source and destination. It is going to reserve the path, but not for all traffic, for some specific traffic. So it needs to now know the available paths, and it needs to know the resource that are left, and then it needs to decide which path is suitable for this traffic. Only after that it can reserve. Please understand what I'm trying to give here. You see, we have various paths, and all are MPLS paths. But some paths are free, whereas others are busy. Whenever a particular traffic comes, you want the traffic to use the path with a lot of bandwidth, which means you are thinking out of box. Why do I say out of box? Usually how the path is determined? By checking the routing table. But here you are not worried about what the routing table says. You don't care about what the routing protocol says or routing table says. You say, I want a path which has got enough resource, enough bandwidth, sufficient bandwidth. You see, the routing table may point towards a path, but that path is used by everyone. There won't be enough resource. Do you agree with me?
Yes, sir, I do agree.
When the routing protocol points towards a path, every traffic will use that path which is there in the routing table. But there may be other paths. There may be other paths which is not elected as the best path, and they are idle. They're idle. They're idle. No one uses that path. Now this RSVP can check the paths, available resource, and it will see which path is suitable for your traffic that you want to give high weightage, and it moves the packet via that path. See, that path may not be a path in the routing table. That path which RSVP is going to give may or may not be in the routing table. Then how can RSVP know? If RSVP is not a routing protocol, how RSVP knows all the paths? First thing. Secondly, how RSVP knows the bandwidth that are available in all paths, and how RSVP can compare the paths and provide the best path for your traffic that you need some special service. If it is not a routing protocol, then how it knows all this info? Without knowing all this information, RSVP cannot do this for us. RSVP cannot find the best path. RSVP cannot reserve the best path for us. RSVP needs info. RSVP needs visibility to all available paths and the available bandwidth. The available paths, when I say the path, even those that are not in the routing table, because the path in the routing table is always used by everyone. So we need we need RSVP cleverer than the routing protocol. Of course, I call routing protocol as dumb. Yes, it cannot do what this RSVP can do. So we need a protocol which is cleverer than our normal routing protocol, because it can even see those routes which are not in the routing table, which can also see the bandwidth available left out, the resources that are left out, and it can also put the traffic that you want it to be on the special elected path. See, it's a clever protocol. It does routing protocol job, it does quality of service job, it does placing the traffic in the path, kind of data plane job, it does control plane, it does quality of service, it also does many more things, you will understand this. So you see, this is router A, and here we got router B, and we got multiple paths, and traffic from alpha, whenever it tries to use the WAN to reach beta, I want special service. I want the path which has got 500 kilobits. The path should have 500 kilobits. End to end, I'm telling you, end to end. There are many routers in the middle. End to end. Quality of service is what I want. I want end-to-end quality of service. What do we call it as? Is it INSERV or DIFSERV?
Not quite sure.
See, DIFSERV is quality of service on every hop. INSERV is end-to-end. Got it? INSERV, integrated service. INSERV. INSERV is end-to-end. DIFSERV is hop by hop. Normally, when people say quality of service, they mean DIFSERV. Have we not covered quality of service? No.
Second?
We have not covered quality of service for you, right?
No.
Okay, you see, DIFSERV is writing commands, QoS commands on every router and telling the router how to treat, how to prefer the traffic, how to handle the traffic. That is DIFSERV, doing it on every single router. INSERV, you don't do it on every router. You do it on this head-end router. Head-end. This is the right term to use, head-end router. See, in this direction, if you see, this is the head-end router, this is the tail end. And if you see the direction of the traffic in this way, this is going to be head-end, this is going to be tail-end. See, traffic engineering is unidirectional. which means if you do traffic engineering in this direction, don't expect return traffic to come on the same path. Why? It is unidirectional. You have to do it on the other side also. This is very important fundamental about traffic engineering. Did you get this point, the last point that I said?
Yes, I do.
Traffic engineering is unidirectional. If you are doing traffic engineering, make sure you do it on both sides. If you expect same path to be a return path. Otherwise, the ongoing path will be as per your traffic engineering, but the return traffic will be according to the routing table. I told you, traffic engineering will not always pick the routing table's preferred path. If the resource 500 KB is not available, if the 500 KB is not available, traffic engineering cannot use the path. See, let us say the routing table has got this as the best path to reach beta. This is the path. Let me call it as path 2, path 1 and path 3. Path 3, which is the elected path? Path 2. According to the routing table, this is the path with the low cost. Assume you are running OSPF. Between router A and router B, you got OSPF. And now the elected path is P2 as per the metric. Everyone is going to use that P2. As a result, you don't have enough bandwidth. But there is a requirement that whenever alpha talks to beta, if 500 KB is not there, the application will suffer. The application which generated the traffic will not work proper. They need guaranteed 500 kilobits. That is where traffic engineering comes into picture. Did you understand why we need traffic engineering? Quality of service is doing quality of service on the elected path. Quality of service is giving some priority, all the stuff on the elected path only. But traffic engineering is using RSVP. RSVP is quality of service on the overall paths. It compares all paths, even those paths that is not there in the routing table. If P2 don't have 500 KB, traffic engineering will put this path, which has got that 500 KB, P1, in the data plane. I repeat, whenever alpha comes to communicate to beta, router A will go and check whether P2 have got that 500 KB. If P2 don't have 500 KB, then it will see whether P1 and P3 have got that 500 KB. Of course, they are going to have it because no one is using the path. Those paths are available but not in the routing table. So it is going to give P1 as the path for alpha to reach beta. But I tell you the secret, none of this router has got routes to reach beta via this path. These routers don't have the routes. Then how they are going to see? They do know that beta is available in this path, but not in the routing table. I repeat again. The routing table don't have that route to reach beta. They may have a topology table or database to they may know that there is a path to reach beta, but it is not in the routing table. So you're going to see traffic engineering moving the packet via a path which is not there in the standard control plane, which is called routing table. It is going to move the packet via the path which is not in the routing table. But if it is not in the routing table, how it is possible? That's a
Exactly.
question that we all should ask. How is this possible? Now, my question to you is, why is the routing table needed in first place when I have MPLS running in my topology? Of course, MPLS needs route information to provide labels in the path. I agree. But who is the control plane now? Is it a RIB or MPLS? Who is in control of path now? Is it layer 3 control plane or 2.5 control plane now? It is 2.5. It's the MPLS, the commander in control. MPLS is what we have to decide the path now. It is the labels, the one which is going to decide the path. That's what I want to say. It's the label. See, we all know that MPLS depends on routing table, the safe table, blah, 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 all those things. But don't worry. Those things are now taken care. You don't need a routing table to provide you the route when you have RSVP. RSVP says, cool guy, cool buddy, I will give you other paths, visibility to you. You don't need to worry. You don't need to wait on routing table to do this. You don't need to wait on routing table to provide the route. I am there. RSVP guarantees I am there. I will give you visibility to P1 and P3. I am there. I'll give you. I take responsibility. It is telling MPLS, cool buddy. If you depend on routing table, it will show only P2. But I, RSVP, giving you visibility to P2, P3 also. So it talks to MPLS. RSVP talks to MPLS saying, hey, you also have P1. Check whether that 500 KB is available in that. RSVP goes and checks it. And it finds that there is a bandwidth available. Now RSVP confirms that, yes, I have the bandwidth. Immediately MPLS says, okay, I'm going to help you by giving label for this part. Label, take this label, take this label, take this label. Use the label and come to me. I will take you to the other side. Use this label. Look at this, how smart it is working. Those paths were not in the MPLS table earlier. So no labels were there for that path, P1 path. But as soon as RSVP and MPLS finds that there is another path with enough bandwidth, label for that new path, elected path, which is not in the routing table, is distributed via LDP. Runtime, I repeat the word, runtime. Whenever alpha comes and it wants to talk to beta, in the runtime, it finds the path. For that path, it provides the label immediately, tack, 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 fast, fast, fast. And the path is now available using labels. The packet moves, not using the routing table. And once the path reaches B, router B, those labels will disappear. What? Those labels of new path will disappear. You got it?
Yes, sir.
So it is runtime. The tunnel, the tunnel which is going to be established via P1 is not permanent. It's temporary. Only when alpha talks to beta, it is going to be there. Once it is finished its conversation, once it finishes its conversation, the tunnel will be teared off. No more labels via that path, via P1. Now, still you did not get one answer for one question. You know what is that question? Who is RSVP? It is not a routing protocol. Who is RSVP to tell MPLS that you got another path type P1 and P3? How RSVP knows this? That is the question. You did not get an answer. Am I right?
Right.
Did you understand the other part? How this is achieved? Or do you have any other question also other than this?
No, not yet.
Okay. Now, who is RSVP? It's not a routing protocol. Then how it knows? See, if you take the RIP, it advertises the routing table, so router knows. If you take EIGRP, it advertises the updates. There is a topology table, feasibility condition, successor routes, feasible successor route. So it knows the alternate path because there is a topology table which maintains the alternate path when the feasibility condition is met. If you take OSPF, it sends something called link state advertisement. With a link state advertisement, it knows the complete topology. So there is a logic, okay? There is a logic there. But who is RSVP? What advertisements they send? If it is not a routing protocol, definitely they are not going to advertise the route. Then how RSVP gets that visibility to the topology, entire topology? That is what these guys straight away come to the point here. I just read this line. I was not satisfied with the words that they have put, so I took you to a long story to make you understand what they have written there. Let's go and read that. Constrain shortest path first. So RSVP allows the use of source routing where the ingress router, what is the ingress router other word? What is the other word for ingress router? In traffic engineering, we don't call it as ingress router, we call it as head end router, head end router, ingress router, head end router. Okay, the source routing where the ingress router determines the complete path. Very important word. Who determines the complete path? The head end router decides the complete. Head end router decides I'm going to go via P1. The complete path through the network. The ingress router can use the constrained shortest path first. What is this constrained shortest path first? Is it another routing protocol? No. It is not another routing protocol. We know OSPF. But here they removed O and they have put what?
C.
C. Is there any connection between OSPF and the CSPF?
Yes.
Yes. Yes. You know what? Not only SPF, this RSVP is going to steal, rob, loot the database of OSPF or ISIS. So one thing you should know that RSVP can work only with OSPF and ISIS because it needs visibility to the entire topology. RSVP works along with link state routing protocol. You understood? We need to go to OSPF and tell, hey OSPF, there is a protocol called RSVP. He needs your support. share your database. So we ask RSVP to go and take help from link state database and form its own database. I repeat, RSVP goes and refers the link state database and forms its own database. All right. So ingress router can use the constraint shortest path first calculator to determine the path to the destination. So if I would have told this without the background story, you might have not got the answer for what
No, I have a
is
question.
written here. Yes, ask the
Okay,
question.
but what if we have BGP in the middle?
I repeat, if you want visibility to entire topology, you need a link state routing protocol. If you have BGP, I don't care, it's okay. You have BGP, but you also should have a link state routing protocol for BGP to work. In IBGP environment, you don't only enable BGP, you must have an IGP protocol, and that IGP protocol should be a link state routing protocol. If you want to have BGP with OSPF, you can have it, no problem. But this RSVP is not going to talk to BGP's database. RSVP is going to only talk to the link state database because BGP will not have the complete topology info. BGP will have only those networks that you have advertised. But link state routing protocol is going to have the complete database of your topology. So if you have BGP, fine, no problem. But you need a link state routing protocol in order to have RSVP. So RSVP is not going to be a problem because for RSVP you don't need to remove that layer 3 VPN that you depend on BGP and you still have the BGP. You can still have VPLS that you were having earlier, all that XConnect and layer 3 VPNs and VXLAN, whatever you want to have, you have. You can still have it. You can also have traffic engineering on top of it. RSVP needs only the link state database, nothing else. Any other question?
No.
Okay, now you see how RSVP gets the visibility by copying the database from a link state routing protocol. We call it as constrained shortest path first. So that is used to calculate and determine the path to the destination. Okay, next. Ensure that any QoS and shared risk link group requirements are met, meaning you need to see if there is any need for some reservation. As I was giving you an example here, 500 kilobits. That's the quality of service we want to ensure. So we are going to tell RSVP that we need a path with constraint. What is the constraint? 500 kilobits. 500 kilobits is the constraint. So we need, that is what constrained shortest path first. We need a path that ensures that 500 kilobits in the path that it is going to determine. Did you understand these things now? So your requirements need to be met. For that requirement, it needs to calculate and find the path. That is why it is called as constrained. In another word, requirement. In another word, ensure the QoS. Right? So again, it is going to use the path and the label provided by RSVP. Yeah. So, sorry, LSP, link state path. It's going to use the LSP. See, LSP is the word we use in ISIS. Link state packet data unit, PDUs. Yeah. In another word, you can also say LSA or link state packets. All right. Now, RSVP, the RSVP optical extension includes an ability to signal optional wavelength and share risk link groups as well as the bandwidth and latency and other link characteristics. Let me explain you this. So RSVP between the head end and the tail end, it signals. What it signals? It signals the risk in this path, the bandwidth in this path. See, you need 500 kb, but RSVP is going to signal saying this path is not good for you. Why? There is no 500 kb available. Everyone is using that path. That is what it means here. RSVP optical extension includes the ability to signal optical wavelength and share the risk link group as well as the bandwidth and latency and other link character. Meaning when they say risk link group, what they mean is all the available paths. In all the available paths, it is going to say what is the latency on this path, how much bandwidth is left in this path, all this info. That is what it is going to signal. From where to where? Signal is from where to where? No. It's the opposite. Head end is what? Initiating the requirement. Now, who has to check? RSVP has to check on all the paths until you reach the tail, and tail end should say, yeah, clear, come this way. It's a route clear path. This path has got some risk. This path may also have a clear, So who is signaling? The tail end signals to the head end which path is the best. That's the logic, right? Yes or no? Can head end signal? Of course, tail end only can signal you, because tail end is the final destination. Yeah, so that is what mentioned here. And Meta shows MPLS software, DC MPLS fully supports RSVP. Okay, so this is what. So what all involved in RSVP? Can you tell me? To have RSVP, what all involved?
Need link state protocol. Yes.
Come again?
Yeah, link state.
Okay, very, very important. Very important. Link state routing protocol. Second.
Need the RSVP itself.
Correct.
The head end and tail end. Need to identify those.
Okay. Next.
MPLS.
MPLS. And then you see, I told you, depending on the constraint, a path even which is not in the routing table will be chosen, and a tunnel will be established. Did I say that? A tunnel will be established. So what is needed is a tunnel interface. You understand? You understand why you need tunnel interface? Because this is not a permanent path. P1 is not a permanent path. See, sometimes P1 may be down. It needs to form tunnel via P3. So tunnel only can use any of this physical path. You understand? According to the availability, a path is going to be selected. It's not a permanent, a permanent path. The path is going to be different depending on the circumstances. So, for example, if P2 goes down, all traffic will go via P1. So now it is going to choose P3 because it is idle. P3 is idle. So you need a virtual interface, you need a tunnel interface so that you can use any of this available path to reach the
So now as
destination.
a,
So did you understand the requirement of tunnel
wait a minute,
interface?
ask a question. The tunnel
Question.
interface,
Ask.
is it dynamically configured or we have to configure it manually?
We have to configure manually, but we are not going to say this is the source destination. You remember when we do GRE tunnel, we say tunnel source error,
Right.
isn't it? Here you are not going to say any of this. This is dynamic tunnel.
Okay.
Now, this is traffic engineering tunnel. The tunnel mode, it's not going to be GRE. It is going to be MPLS, traffic engineering tunnel. Okay. So configuration part, if you see, you will be more clear how this functions. Now, next thing that I want to tell about this is you can also have
Path options?
what is this? Yes, correct. You can also have path options. You can say, hey, even if bandwidth is available in P2, which is according to the routing table, best path. P2 is the best path, I told you, according to the routing table. Even if bandwidth is available, I don't want that path. You check first P1. If P1 is not available, then you check P2.
Right.
You understand what I'm saying? You can have the path option. You can say, this is the path I want. Whether the default path has got enough bandwidth or not, I don't care. I want you to check P1 first. If P1 really do not have, then you can jump to dynamic. If dynamic also don't have, then you can jump to other paths. You don't need to say P3, you can simply say other paths. So you got something called path option. Next, there is something called fast reroute. What is it? Fast reroute. FRR. Fast reroute. FRR you might have seen in some documents. FRR. Fast reroute. It's nothing but again signaling. See, after designing this path, if something goes wrong here in this link, if the link breaks, there will be a signaling immediately. So it can immediately swap all the remaining packets to the other path. See, P1 is the path elected by RSVP, not by the routing table, by RSVP. After electing, let's say 500 packets to send, 100 packet is already going, but there is a break in the middle. While it was going, there is something wrong. Where happened just like in the runtime, something went wrong. So the remaining 400 packet will be immediately swapped to another path if you enable fast rerouting. In short, if I want to say, if you enable fast rerouting, RSVP is going to find more than one path, so that if that one path goes down, it can use the other path just by swapping the traffic to another link. And so it is going to maintain two labels. One, primary elected P1. If that goes down, I need to take another label given by this path so that it can go this way. You understood fast reroute?
Not exactly.
No worries. With the table, fast reroute is very advanced. First of all, let us do normal traffic engineering. And then we will go with that small feature called fast reroute at last. You will understand when I explain with topology. So in another word, if I need to say fast reroute, after you decide in a path, when the packets are flowing, if path breaks, the remaining packets that need to be sent will be placed into another path. When we say placed into another path, it is not that easy. You need to know the labels of the other path. You need to establish this tunnel over the other path. So, which is not possible when the session is on. So, precautionarily, it takes the steps. Like when it selects the primary path, it also keeps the secondary path ready so that when the primary path goes down, it can swap the traffic to the secondary path without sending the signaling and waiting for the signal from the tail end. It is ready with the backup, like you have in like you have in like EIGRP, you can say, to be more accurate, like you have in RSTP, RSTP, STP, RSTP. You remember rapid spanning alternate path. So these are all the things that we are going to see in our lab in our next class.